Okay, so this problem right here is called as the indivisible permutation, and what indivisible mean is that the thing or object cannot be further divided into smaller chunks, so like that. So in this problem, what we're given is an integer n, and n is a number, and then what we have to do is based on that n we have to construct an array, which is going to be named as p or whatever you like to call it. But here in this problem statement we say it as p. So what those two things mean is that the p is basically the permutation. We have to create an array of permutations of what, of the first n natural numbers, and that n is given into the input side. So for example, if we have been given n is like, let me open up my whiteboard, blackboard, what do you say? Okay, so if the input is given as 4, n equals, so what we have to do is to create a natural numbers, and first n natural number are, and natural number started from 1, not from 0. So 1, 2, 3, and 4. So this is what we're going to have based on that n. Okay, and what we have to do is to create some permutations, and what those permutations are is a thing which we have to see. And yeah, two other points which they also mention is that, for example, if here, oh, I was going to explain it. So those permutations is nothing but is the rearrangement, and that's what basically a permutation means. It's the rearrangement of the very same thing. So if first n up to n and the first n natural numbers are there, so you cannot have anything which is exceed or above that ends. For example, if the threshold is up to 3 and if the n is 3, so 1 2 3, that's it. You're going to always going to have 1 2 3 or 2 3 1 or 1 3 2. Not never going to have a 4, or you're never going to have some repeat integers. So these are the two really important points in this problem. And so here what the indivisible means, because now we have discussed what permutation is the rearrangement, but what indivisible means is further not being able to do it. And what is the rule or the constraint that they are giving us is that the position I, the smaller I basically refer as the positions, and if it is in loop then we usually use ing in loop case, but if it is with the case of array it's always going to be with the position. That's some sort of standard that we have. So the I does not divide p sub I, and what p sub I is the position of the at that position, that array, the p array of that array, at that array p, the position of ith, the element at that ith position cannot be divided by the index itself. Well, basically the index is going to be a 0, but here, they are assuming, or they have told us it's a 1 base index array. And here for every index which is started from 2 up to n, that's a thing, less than equals to, from 2 to up to n, like so. For the first index we can have it like the same digit law. Oh, that means that we can have one at the very same digit, one digit at the very same place, but 3 and 2 cannot be at the same place because they like, then the 2 could divide 2 and 3. What they mean is, if we have given input like 1 2 3, what we have to do is we have to interchange their positions, or like uh well, see, we can also do that. We can place 1 here, 3 here, and 2 here. That can also work. So the output here could be is 2 3 and 1. That's a very one answer to it. Okay, but further, let's look. That's a very that's just one answer. You can have like multiple. So another answer that which they have given is, I think, 132. You can also have it because the first index is not relevant that much. The constraint is started from the second index onwards. That's what the problem statement is saying. So that was the rule for the indivisible. Okay, so we have like understood the problem statement. Now the two things here which came instantly in my mind is swapping, because we basically is doing arrangement, rearrangement of the very same integers here. Okay, so how are we going to do it? So something which I remember in my college days is that from quants or reasoning, I don't know, so lectures which were provided for, solving building some sort of logic systems, or decoding, coding, decoding, whatever that is. So there I remember is that, for example, if we take, no, let's Hmm. So there are two things that hit instantly in my mind is that the rearrangement, and second is the size of the array, or basically the n is going to be even or odd, because if you're doing some sort of this rearrangement thing, the if you have like odd digits or the odd number, how are you going to deal with that one single digit? What I mean by that is, let's look. For example, if n equals 6 here in this case, and n equals 7, let's take two cases. So if n equals 6, that means 1, 2, 3, 4, 5, and 6. And here it's going to be natural number is 1, 2, 3, 4, 5, 6, and 7. Okay, so we have to do some rearrangements. And the very first instinct which I got here is like, how about swapping the first two digits with each other, then the next two digits with each other, and the last two digits with each other. Fine. So what it is going to become is that 2, 1, 3, 4. Oh, wait, no. That's going to be 4, 3, yeah, and 6, 5. Okay. So if you look at indexing here, 1, 2, 3, 4, 5, 6, none of the index divides itself. If we like don't care about this particular index, that 2 doesn't divide 1, 3 doesn't divide 4, 4 doesn't 3, 5 doesn't 6, and 6 is 5. Okay, so we were able to do whatever is asked us in the problem statement, and we have achieved that very answer. I think this is a right answer for that. But the problem arises with this case particular, when you have, odd digit here or the odd number as n. So if you started doing this thing, very same thing, that you're gonna stuck up here at the very last digit. So what I came up with is that some sort of a merge sort logic, or dividing the array in half. So what we can do here is that we can swap these two together. Okay, and then with the last thing, what we can do is either we can do this or anything like that, which doesn't go is like, it's a very basic idea. I didn't did any much more thing in it. And wait, so let me write this: 2, 3, 4, 3, 7, 5, and 6. That could goes well, because if you do 5 and 6 again, like, it's gonna create a problem. That's a one approach here with the odd case. There could be one other approach that you can take is how about since you can do one more thing. Instead of touching the last digit at the very end, how about touching the first digit with the odd case? I mean, we can do with the very same logic with the even one, but how about doing the first digit? Like, how about changing its position at the very first place? Or how about, just instead of building the array, how about just printing one, and then like doing the rest of the things with, 2, 3, 4, 5, 6, 7, doing the very same thing with the remaining elements, like this, whatever we done with the even numbers, the case for the of even number, because this is going to result in the very same thing if we just left one as it is. Because see, the first position doesn't even matter. It never been the case of bother to us, because you see, the case is started from 2 and 3. The constraint is from the second index, not from the first index. So that's a thing. So what we can do is to print 1 again here, a, then 3, 2, 5, 4, and your 7 and 6. Wonder, amazing. So I think we were able to have our answer here again with the odd case. That's a very basic approach that I've taken, and you see that it's the very same thing here in the second half, and you just can print the very first digit in the odd case, and you can do the very same thing in the other cases. Or if you, since we have here eliminated, um you can do yeah, okay, let's try to build this one at first. Let's have some a little bit of difference up here, and let's try to build this one. The approach I think we can do is hmm so let's try to build, yeah, let's go. Where are we? Yeah, so what are we given? Where's my keyboard? Okay, so the case is hmm we're given n and p. We have to create p, so we have to take n, and I think we don't have to take anything else, isn't it? So just take n here. Then we have our two cases, even and odd. Okay, so let's first you can you see you can make any case if you want. So I'm go with even or odd. Let's see, let's go with even first, because I think we don't have to deal with the first odd digit at the very first place. Or maybe we can go with odd one, there is no problem with that. If we go with odd one, it's somewhat like, oh, what we had decided is not equal 0, so that's the flag check for the odd number, whether the number is odd or not. So here we're making sure the number n is going to be odd. And here let's we printed 1 at the first place, so cout 1. You can also type 1 as it is, it's up to you. Then what we have to do is to create the remaining first and digit natural numbers. That's of I think the remaining part is, so int I, since index equals here, it's an odd case. So for the odd case, 1 is been here, 1 has already entered the if clause, 2 is not going to enter, so the 3 is going to enter. So the our next case is starting going to be from digit 3, n equals 3. So that's the case. Then I less than equals n, I plus plus for the increment, plus plus, wait, no, not the plus plus, because if you remember what we did is what the yeah, if you remember, we swapped two digits at the very in a one go. You saw that, like two digits and two digits after printing 1. So what we're going to do is going to step 2, we're gonna increment by 2, since we're printing 2 at the very same time. So cout we have to interchange the positions, isn't it? So I is 3 and 4, we have to swap 4. Oh, we can do that too. Here going to be I, and here going to be I minus 1. I think so. Why? Because we're printing here what? The first thing is going to be 3, then 2, then 5, then 4. Okay? Yeah, that's how it's going to print. And fine. Anything else? One more space. Do we need one more space afterwards? Maybe. Uh, yeah, maybe it's not going to hurt. So let's just have one more space here, and that's done. I think that's the odd case. I don't think we have to do anything else. Let me type here odd. Now the remaining case is for even. Now for even, we're going to have else clause. Here we're going to have a for loop. No, instead of for loop, for even, okay. If you look here for an even case, which is starting to, the only option we have for the very basic case is that we have to swap 2 and 1 with each other. Why? Because this 2 is going to be fall on the second index, and if it's going to fall on the second index, what we have to do is to swap those. And since we are not building the array, let's just print. Okay, so this is gonna print, then 3 is already been dealt with on the uppercase. Now the remaining case is going to start from 4. So int I equals 4, and I think the rest of the thing is going to be same. So less than equals to n, I plus equals 2, fine. And then here we're going to print the values. I think it's going to be the same, because we're just going to interchange with each other. Yeah, so it's going to be cout I minus 1, another space, and I think we're done. Now the only thing which is remaining is, after completing the case, we have to print a new line, since a new line is been there. So slash n, I'm not using handle. It's kind of, it actually takes a little bit more time in execution since it's a call, system sub call, so we're not taking that. I think we have done that. Yeah, art case and even. Let me just write even here. Yeah, compile and run. Hopefully, I think I didn't made any mistake. It worked. It worked or not? Yeah, successfully executed. 21132. Oh, that doesn't even matter. Answer is going to be different. We can have like any valid answer to it. Yeah, that's correct answer. Okay. Fine. So we have done with first solution. The very first approach is just looking at the and whether it's going to be odd or even. That's a important thing which hit at the first. Now, second thing which we can improve in this solution is, since, hey, look, we are not building any index. Oh, my index, man, database, god, we are not building any array here. So since we are not building and we're just printing, what we can do is to do one thing which is a little bit clever. I think it's gonna save one more loop and if and else clause check. So what we can do here, where is it, is to make it somewhat like, since, hey, look, what we did with this case, instead of taking this color, let me change. Okay, so here if you remember that we were, changing the position of 7, or maybe we can um, remaining, though we are not changing the position of 1, but we are like started swapping each other element or just printing them in this fashion. So instead of doing this, what we can do is a little clever, not too much. Well, what we can do is to, we just change the position of the very first element to the last and just print the remaining elements as it is, and see, it's going to work with any case, whether it's going to be even or odd. So that's the even case and that's an odd case. If you take 1 here at the very end here and you just paste the remaining elements after here or at the first place, or whatever you like, or maybe you can like just print the last element at the first, that could also work. I think that's much easier, I would say, instead of printing the first. Yeah, that could be really good. So what we can do is to, print the very last element at the first place, and then remaining 1 2 3 4 5 6. That's the case for n equals 7. And if you look the indexing, so 1 2 3 4 5 6 7, none of the index matches with the same thing. That's the very constraint at which we or successfully be able to manage to handle successfully to handle to we were successfully to manage to handle this particular constraint here. So let's just improve our code a little bit. It's not going to be too much, but where is it? What the, wait, where am I? Indivisible permutation, yeah, got it. So just remove the else clause and then remove this if clause. Instead of printing this, what we can do is print n and then have a space, and here we can start our loop from 1 less than n and I plus equal 1 or plus plus. It's gonna save a little bit time, nothing much more. And I think we can swap, or if you don't even swap, it doesn't even matter. Wait, all we have to do is to print now. I think that's it that's all it's going to do. It's gonna work. Let's see. Did it? Hopefully. I think, yeah, I think that's it. We have to do in this problem, indivisible permutations, is we just have to make the permutation in a way, the rearrangement of the digits in a way that it doesn't even matches the very same index. That's it. That's all what we have to do in this. You see the time is reduced quite a lot. So that's the thing. Okay, goodbye. Let me stop this stream.